Welcome everyone once again to the FusionEPtalks, a student-led webinar on fusion science and technology. My name is Dhaval, and it gives me immense pleasure to introduce Professor Dr. Ewa Pawelec. She graduated and received all her scientific degrees in atomic physics at the Jagiellonian University in Cracow from Poland. She uses spectroscopy either for plasma diagnostics or to measure atomic and molecular parameters. She has worked for some time with low temperature plasma, welding arcs, plasma jets for atmospheric entry simulations, hot thrusters, etc. But around 2015, she started working with high temperature plasmas and has since made some work on other machines, but mostly at the jet for the analysis of visible and VUV spectroscopy and the Tokamak experiments. Atoms, ions, molecules, whatever there is available. And that's what she's going to talk about today. The topic of today's masterclass is the spectroscopy study of molecules, which is not simple because the spectra are complex. But on the other hand, it provides data on the creation process of the light-emitting molecular states. In this presentation, examples of the spectra and the analysis will be taken from jet experiments and comprises different isotopologues of hydrogen molecule and beryllium and nitrogen hydride. It will also be shown how those results contribute to better understanding of different processes happening in the low temperature regions of the magnetic confinement fusion plasma. So without further delay and spoilers, I will now mute myself and hand over to Professor Pawelec. Welcome everyone and enjoy the talk.
Thank you very much. So you have stolen one slide already, but that's okay. So that's what I'm doing at Tokamak, but I would say that molecular spectroscopy is something that is happening in many other machines as well. So it isn't so machine specific as it would mean. So the plan is I will tell about the molecules, where do we find them and which ones, at least which ones at jet, but it doesn't mean that only that in the other machines we cannot find slightly different ones, but that will be how they are produced and why they are important. So what is really the meaning that we are finding those and different molecules. Then I will talk a little bit about the molecular spectroscopy and especially how the molecular spectroscopy differs from the atomic spectroscopy, because this one is much more known for different plasmas, including the high temperature ones. And then how do we study, and especially about the shape of the molecular spectra, because they the distribution of energy on the wavelength, meaning the shape of the spectrum, can tell us many things about how these moleculars were created, how they are going to dissociate, and therefore how they are influencing everything that happens around. And examples are from the most popular things in jets. So beryllium hydrides, hydrogen molecules, and in this case, nitrogen hydride as well. So let's start with the fusion plasma and where do we find those molecules at all? Here is the cutoff jet, and you can see that in the visible range, it's not much that we see really during the jet pulse. The light is only concentrated in the divertor region, slightly up, and sometimes on very close to the walls. And that's more or less also where we can find molecules close to the walls. So not in the core where we have the temperatures of around 10 keV, not in the pedestal when it's around 1 keV, but outside of the scrape-off layer, outside of the separatrix. The separatrix is the last closed magnetic surface, and what is important in the molecular spectroscopy happens outside of that, because we have the ions escaping the core escaping the pedestal and encountering the regions where the temperature is much, much lower. So in the core, we have only completely ionized hydrogenic species and traces of impurities, and also completely ionized low mass light impurities. Those are here again like in jet. But of course, in the other machines, we will find carbon, we will find boron, depending on which machine we are talking about. We have also highly ionized metals, mostly tungsten, but that's a story for another time. In the pedestal, we have hydrogen ions and impurity ions. And in the scrape-off layer and external regions, there we get everything. So we do get ions, we do get atoms, we do get molecules, and most of those molecules will be containing hydrogenic species. So any kind of isotope versions. This is one of the rare examples of the measurement of temperatures outside of the separatrix. And you can see that on the in the region of 30 millimeters, scope which is close like that, in this very, very thin skin around the plasma, we are getting from the temperatures of over 100 electron volts to the 20 electron volts and lower. So we are getting close to the region where the molecules can still be. This is more complex that it could be thought to be, because molecules, if they appear on the wall, they do not disappear in a moment. They live for a moment, and this is something we can see. So where do we find those molecules? In jet, we have a tungsten coverage on the divertor. We have a beryllium on most of the other walls, and we have the hydrogenic plasma inside. So what we get is mostly everywhere around we have hydrogenic molecules, because they are put in by seeding, by fueling, and also they recycle. So if you have already the ions and the atoms from the plasma, they will recycle from the wall, forming molecules. Those molecules may have different properties if we compare them to the molecules that come from seeding, from fueling directly. Of course, in the plasma, if we mix the isotopes, and we do it frequently, well, the ultimate plasma is the DT plasma, which means the deuterium and tritium. So we have the mixed molecules, and they are frequently more in such a 50-50 DT plasma. The GT molecule, the mixed one, is more populous than the pure molecules even. Of course, we have those metal hydrides, or the wall hydrides, meaning that the hydrogenic species are interacting with the metal on the walls, and they are forming the hydrides. And such hydride is something that is normally formed by so-called chemically assisted physical sputtering. So we have the hydrogenic species arriving and forming those hydrides. They are mostly short-lived, but they still appear, and they participate in the wall erosion. So we have in jet we have beryllium hydride and tungsten hydride. Of course, the tungsten hydride will be in the divertor. We can have also the nitrogen-containing molecules, because jet is from time to time nitrogen seeded. So then we have we could have nitrogen molecules, but we didn't observe them. So they probably are very fast changed into N2 plus, which is the nitrogen molecular ion, which we did observe. And we have also nitrogen hydrides created by the surface reaction in the plasma. So they, of course, participate in the production of the excited and ionized species, atoms and ions. So this part has to be taken into account in all the modeling. And also the production is a very important part of the plasma wall interaction. So the low temperature plasma region there are two which are slightly different. There are limiters and all the other walls around the plasma where we have a separatrix and we have the ion flux to the wall through the separatrix, because of course the separatrix is a boundary but not imperious. So there is an ion flux and atoms are going to the wall and molecules are created and getting back. And also we have here many impurities, mainly beryllium in the jet case. So this production of molecules will be therefore not exactly as we would expect, for example, in low temperature plasma. In low temperature plasma, we do not have very highly energetic ions. We have, in many cases, highly energetic electrons, but ions are normally relatively cool. In the fusion plasma case, we have the very energetic ions impinging on the wall, and that was why those molecules may have a slightly different features that we normally observe. In the case of the divertor, we have relatively cooler plasma, especially in the detached divertor. And we have here two very, very strong fluxes, which are along the separatrix. So here on the so-called strike points, we have very, very strong fluxes. And here, everywhere, we have also those fluxes that go through the separatrix. And then we have, of course, many fueling molecules that may be also introduced from outside in this region. And seeding, in many cases, is also done into the divertor because we want a seeded plasma in the divertor. So here we have a very, very complex plasma with very strong gradients, with the temperature, density of the electrons, density of everything else. We have very high fluxes, and we have the molecules that are penetrating back into this hot plasma. And this penetration is centimeters from the vessel wall. The observation in jet is not bad, but not ideal, meaning that we have the spectrometers looking in the divertor region, observing the divertor and the divertor throat up. And we have the spectrometers observing the walls, mostly the inner divertor, the inner limiter here around the level of the midplane, slightly up over midplane, slightly lower as well. There are many, many lines of sight. And we have also visible spectroscopy observing the outer wall. It's not that they are not really spectrometers planned to observe the outer wall. They are used for charge exchange, but they also see the outer wall. Why I am talking here mostly about the optical emission spectroscopy in the molecular case? I get this question many times from the molecular spectroscopists because they are used to absorption spectroscopy. But doing the absorption spectroscopy means that you need to go through, which isn't easy in the fusion machine. So optical emission spectroscopy is easiest because it's passive, it's relatively easy access. It can cover many, many species if you have relatively large wavelength range, and you are observing in this place where you are looking at, because as I told you, the molecules are in the very thin layer, so they may be observed that way easily. So, so the absorption spectroscopy, laser spectroscopy is not necessarily better in this case, and it's definitely much more complex from the technical point of view. Total intensity. So what we are mostly observing is the total intensity, which is proportional to the radiating particles along the line of sight. In the molecular case, it's mostly the very thin layer, but not necessarily in the divertor. What are the particulars of the molecular spectroscopy? Well, let's begin with the beginning. If we have an emitter and it has an upper level and lower level of any kind, and we have electrons that can go up or down, it may not be even electrons, we can generate light. This light is mostly shown as something called a spectral line, which has certain features, which is the position, width, and shape. In the case of molecules, we mostly do not care much about the shape of one molecular line, because as you will see, we have thousands of them. So mostly the shape of the molecular line is determined by our spectrometry, by our optical apparatus. Position and especially intensity is what is important in the case of the molecular lines. The intensity is proportional to the population in the upper state, so we cannot probe by optical emission spectroscopy the lower, the base, the ground states, for example. That's a completely different story, unfortunately. So comparing the atomic and molecular spectroscopy, we can see here the atom example. We have, for example, beryllium, as we do in JET. We have the beryllium plasma spectrum, and we can see a relatively low number of the lines we observe here. In fact, those are the lines from the beryllium atom and ion that are the strongest in the JET spectrum, because this is the wavelength region which is easiest to see there. And we can see that they are the transitions between certain very well-defined levels with very well-defined energy. In the case of the molecule, here you have the the beryllium hydride as an example, and each of the electronic levels that you have here as a particular one energy, here is the energy curve, meaning that the energy of the electronic shape, electronic state, is depending on the separation of the nuclei in the molecule, and these are always changing. The molecules are always moving. Also, the cores are moving within the molecule, so the energy of such molecule is changing all the time. And those energy levels then are very not one energy, but the energy that depends on the separation of the nuclei. And this is the wavelength separation that gives rise to the visible light. What's more here is that if we start to look within these electronic transitions, we can see that each of them is divided into sub-levels. In the case of atoms, it happens as well. For example, the subtle and structure. But here we have it much more because we have the quantification of the movement of the nuclei in the molecule. So we have the vibrational levels, which are connected to the fact that the nuclei are oscillating, and we have the rotational levels because the molecule can rotate according to different rotational axes. And the distances of such levels in the energy or in the wavelength region are as if you transmit between the vibrational levels in the same electronic level, that will be in the far infrared, and the distance of the rotational levels in radio frequency. But if you have the visible transmission, then you will be changing the electronic, vibrational, and rotational levels. So you will have many lines from one electronic transition. Here are some equations how to calculate all of that, because it's of course incredibly complex, and you can, in principle, and there are places like that you can find such data. You can find the data which are which show you every molecular level as a separate one, but you can also calculate the energies of those sublevels from such an expansions with the vibrational numbers and the vibrational coefficients, rotational numbers and rotational coefficients, and the level population in the molecules in the plasma. We mostly assume are Boltzmann. Assume, because we can check it, of course, and it's not always looking totally Boltzmann, but more or less. If we want to have it more correctly, we are doing all the plasma modeling and putting the different populations up. So we have, of course, the partition function over that, so we can calculate the intensities, how those intensities are going, and nuclear spin influence makes us also sometimes makes some lines stronger or fainter. And that's another thing, especially is visible in the homonuclear molecules. You can see here one example of how such spectra look like. These are relatively high resolution spectra of the beryllium deuteride, the most popular molecule in apart from the hydrogen that it's visible in jet. You can see here that if you change the vibrational or the rotational temperature, the shape of such spectrum changes, and very much. So you can, by measuring such spectrum, you can fit it then and get the temperature of certain subsystem out of that. And then it can go to the modeling, to our understanding of all of that, and so on. So band is one electronic transition, and these are band set, and there are bands from different vibrational transitions, and then are lines, rotational lines within those transitions. One very important thing in the case of the molecules is that they have very strong isotope effect. because in the case of atoms, there is an isotope effect, but it's very, very subtle. You have to really have a high resolution to distinguish even between hydrogen and deuterium, which is the easiest. For the heavier elements, distinguishing between isotopes is even more difficult. But in the case of the molecule, it's visible very, very easily, because the separation of the vibrational and rotational levels, and therefore rotational and vibrational lines, is dependent on the reduced mass, which means that in the case, the differences between hydrogen, deuterium, and tritium are by the factor of 2 or 3, meaning that in hydrogen we have the reduced mass of half, in D2 we have 1, and in tritium 1.5. Therefore, if you have the spectrum of hydrogen, this is a molecular hydrogen spectrum, so-called the Fourier band, which is in the visible range, so we like it due to that, and around 600 nanometers, as you can see. And you can see that the lines here in hydrogen, from the same rotational transitions, from 0 to 1 and so on, are have certain separation. But when you go to deuterium, and the same colors here mean the same colors, same transition, you can see that the lines are twice denser in the deuterium case. So distinguishing if it is a hydrogen or deuterium molecule, it's very easy, because you see it simply if you have the spectrum, which isn't even that much highly dispersed. In tritium, it's even more. Tritium is even denser here. So let's go at the end to the examples that we have really in JET, and what do we use those spectra for? Because for now I was talking, where do I measure them, or where do we measure them? What is the theory of the molecules? So how do we get those temperatures that we want, mostly for modeling of that? And now, which importance those molecules are. So in the case of the beryllium hydride, it tells us about erosion. You see, in the fusion machine like JET, which is covered by beryllium, the erosion of the wall is very, very strong. Namely, in the carbon machine, it's even worse. Beryllium is eroding, but not as much as carbon. Still, we have then erosion and redeposition of the beryllium during the pulse, during different phases of the pulse. But it was discovered some time ago, but by Sebastian Brzezinski, that there is a part of sputtering, part of erosion, that goes not by only physical erosion, that you have the impinging ion and goes off, and that's all. But you have first the creation of molecule, and then this molecule is dissociated, and you can see what you can see a beryllium atom or ion, mostly ion, because that's how the dissociation works in this case. You can see it here, why it was important, because when Brzezinski has measured it some years ago, I think, 2014 and 15 nuclear fusion publications, you can see that the beryllium deuteride spectrum, which is here close to 500 nanometers in the green, was changing its intensity enormously when the temperature of the wall was changing. So it could have, and also when the intensity of the band was changing, the intensity of the ion lines from beryllium was also changing. So the erosion was different if we had this different wall temperature. And it looked to be that it is based on the differences in how this chemical assisted erosion works, not with how the physical erosion works. So, for example, if we have a hot wall, we have suppressed a significant part of the erosion, which means that knowing how those molecules behave and how we can avoid them is also important to have as small erosion as possible, because that's what we want in most cases to have. We have measured the different isotope version of the beryllium hydrides, and they are pretty similar for different isotopes. You can see here that we have measured, for example, beryllium hydride, beryllium deuteride, and beryllium tritiide, however we would call it, tritiated version. And you can see that the rotational and vibrational temperatures are relatively similar. Rotational around slightly below or some way below 4,000 Kelvin, and the vibrational higher than 4,000 Kelvin. This is also the fact that we wanted to compare those isotopes, so the density and the temperature were of the plasma close to the wall, we were trying to keep relatively similar. It may be from some density ramps, changing density experiments, there may be a change of those molecular parameters, but this is still under study. Here you can see the I would say summary of what we know about such temperature dependence on the erosion due to chemical assisted physical sputtering. And you can see that the hydrogen and deuterium cases, hydrogen and deuterium molecular band, are behaving very, very similar in the dependence on the surface temperature. And you can see that both of the beryllium ion atom and beryllium ion are also descending with the temperature due to that. So we are suppressing part of the erosion. Of course, the isotope dependence of the physical erosion is very high because it depends strongly on the isotope mass. In the case of the chemical assisted physical erosion, CAPS is similar for different isotopes, which is also interesting. It may be that tritium is more different than we thought, but that's, as I said, still in the last stages of the study. So that was erosion, but in the case of other molecules, we have many other things. In this case, this is a study of the density ramp in hydrogen, and the observation is in the divertor. We observe the bands that I've shown you for the as an example of the isotope effect. The bands of Fulcher bands in hydrogen, because this one is a hydrogen low L mode density ramp. And it appears to during all of that study that the Fulcher bands are really dependent on the divertor state. So especially on the things that we call the detachment. Detachment is that we are, let's say, diminishing strongly the flux of the ions to the strike points, those places where the separatoric ends in the divertor. This is a very important thing because we don't want the divertor to melt. So the idea that if we have a very strong pulses, very high energy pulses, we want to get the detachment in the diverter, so buffer in the diverter that will be stopping those ions. And it looks that the intensity of the Fulcher bands in the diverter are strongly dependent on density, but not in any linear way. You can see here that the intensity during the intensity of the part of the Fulcher band that we were studying is relatively flat during the density ramp. Here is the very beginning, and you can see that there is a very luminous dot, but then it descends in the place where we have the strike point position, and it goes outside of the strike point line. This had been also observed in the other machines, so it's not the jet specific thing only. If we go into more details of what is happening there, we can observe different part of these Fulcher bands with different vibrational transitions. We can measure the rotational temperature, and we can see here that the rotational temperature grows during the transition, during the density ramp, to the certain level. At certain point it looks that it saturates or plateaus, but the intensity, at least close to the strike point position, has a very sharp maximum. So if we go through with the density, there is certain maximum intensity which may be strongly connected to the detachment situation. And that's something which is now under study in different machines, not only in jet. Which was first, because this was the first measurement I have done, and that's the last example I'm showing. When we had the nitrogen seeded pulses with certain movement of the strike point position, so-called I don't know at the moment, sorry. We were moving the strike point to spread out the heating of the divertor, and you can see here that the intensity of the molecular band was strongly dependent on what we have here, and also the temperature. Rotational temperature of such band was different close to the strike point and outside of the strike point. The study of the nitrogen hydride was very important for these certain ideas of the nitrogen seeding, because the problem that we were observing was that nitrogen is very nice, at least for the relatively still small tokamaks, as it improves confinement. But the problem is that if we put it with tritium, we get ammonia, which is a stable molecule not like beryllium hydride, for example. Beryllium hydride is not a stable molecule; it will disappear. But but ammonia, especially containing tritium, may escape from the plasma because it's a stable molecule, and may stay somewhere in the ducts, in the pumps, and therefore making them radioactive, which is nothing that anybody would like to. So in summary, we have many places in the Tokamak plasma where there are relatively large quantities of molecules. We can observe them by optical emission. They look mostly very complex as large bands containing thousands of lines, with the Boltzmann and non-Boltzmann distribution within those molecules. So we need specific models for that. And such most important in the case of jet are the erosion connected metal hydrides. There are fuel molecules and recycling molecules from the walls, hydrogenic ones, and they are created from the seeded impurities like nitrogen hydrides. And that's the story for today.
Thank you so very much, Eva, for the wonderful talk, for the insightful talk. We will now open the session for question and answer. The raise hand gesture button on Zoom will allow us to maintain a queue in an orderly manner. So please feel free to raise hands, and I will provide you an opportunity to ask questions in the order of hands being raised. While I see no hands being raised, I'll have a question myself, since I have worked a little bit in the section of spectroscopy during my small career so far. The idea of molecular spectroscopy is something that I had not touched upon, so it was quite interesting for me to see and hear all these results. How difficult it is for someone who is just starting up? How difficult it is to, like, let's say, dive in head first straight into the field? Since you have been working for such a long time, I'm pretty sure you could give some useful insight in that regard as well.
You know, in principle, I'm not a molecular spectroscopist. I'm an atomic spectroscopist.
Okay.
This is what I've learned in the university. Simply, and I don't think I ever had a course in molecular spectroscopy. The idea is that the line is a line, and the only difference is that you have very, very many of them.
Right.
So the main problem is the complexity of the spectrum. So you very rarely have the possibility of making, for example, a Boltzmann plot, meaning that you can distinguish those lines separately, and you can treat them the same way that atomic spectrum is treated or the ion spectrum is treated. It can be, for example, those lines here in the hydrogenic molecules. Those are really nearly separate transitions, and you can treat them exactly as an atomic spectrums and make the Boltzmann plot, make it all, and that's not very problematic. It's more problematic when you have the spectrum that looks like that, because you have many lines that overlap. But then you simplify it by the fact that you are saying, okay, so we have all of them are Boltzmann, and we are fitting the spectrum as a whole. If you have enough data, I have managed to make my my student doing engineer thesis to fit that and to use the data that are already present, because the main thing is to get the data about the molecules, all the coefficients that are needed. But that's not something very difficult, and the learning how to do that is not that difficult on your level, because of course if you are the older you are, the more inflexible you will be. So in this case it will be a problem to changing, because people are looking at that that's so complex, and it isn't really. The main thing is simply to understand that you have to take them as a whole and fit that. But it's just a spectroscopy as any other.
Right. No, I just vaguely remember. I'm not so sure. I might be totally wrong, but when I started up in cold plasmas, I was working with an RF torch, and we were measuring a spectra, and then we had to do some Abel inversion to arrive the the Boltzmann plot, and I was just in the second year of a bachelor, so I found that task quite daunting at that time.
Well, this is something we don't do here. I was specifically pointing out that the molecules here, mostly, in most cases, it's not always true, are present in very thin layers. So in principle, we are treating them as point sources. So no Abel inversion, no problems that you are integrating it along the line of sight, because in most cases you will have them simply in one point along the line of sight, where the line of sight is just crossing the region that the molecules are present. It may be sometimes in the hydrogenic case. It may be that if you, for example, look very much along the line, you along the wall, for example, you can have the integration along that, but that's all. So it's easier in that way, because you do not need to really think of them having a specific a shape along the line of sight.
Right. Thank you very much. Thank you very much for solving the queries. Anyone else would like to ask any questions? I saw a couple of attendees joining almost at the last moment in the beginning of the question and answer session, but please feel free to raise your hands. And if you would like, okay, I see a hand is raised. Or no, is it? No. If you feel like you can also write me a message. Yes, John has a question. I'm asking John to unmute, and if you want also, you can start your video to ask your question.
Hi, sorry. I don't have a webcam on my computer currently. Hope that's okay. But thank you very much for the talk, Dr. Pawelec. I was just curious about what the sort of simulation status is for modeling the distribution of vibrational excitation at the moment, sort of in the divertor, because I know that's an area of interest, but I'm not sort of very well versed in it.
Well, till now, many of the codes like Irene or others do treat the molecules pretty, I would say, in a rough way. Simply the number of molecules and so on, but they are trying to transfer now to the at least vibrational result situation. The rotational one that may arrive later, but at least the vibrational is already done. And I know the group who is at the moment, at least for hydrogen and light hydrogen, because as I said, the isotope effect is pretty strong. So in hydrogen, they were doing the trying to model all of that, with it, including rotational ones. Of course, they need the electron temperature and so on, but they are putting all of that, trying to put all of that.
Okay, thank you very much.
Thanks a lot, David, for the John, sorry, for the question. Then there's a question from Agatha. Again, I would now allow you to unmute yourself, and if you would like to open your webcam, you're welcome to do that.
Hi, Dr. Pawelec. Thank you so much for your talk. I'm first year student at Open University. I'm just starting physics. And I'm considering a atomic spectroscopy or a molecular spectroscopy as a point of interest. And are there any tips that you could give me or anyone that is considering starting a career in that, where to start or what to look for, and how not to be discouraged if things go wrong?
Well, you know, main thing is being a spectroscopist is in many cases best not to totally specialize. So what I am doing molecular spectroscopy as a part of my work, but I'm doing also atomic spectroscopy. I'm doing also ion spectroscopy, VUV spectroscopy. So of the impurities. So simply try not to specialize and try to be interested in many species. The molecular spectroscopy in the fusion plasma, this is something that is now more and more visible, because I think the modeling codes are reaching the level when they need this molecular input. So that's really something that will be needed.
Okay, I don't see any hands being raised. So with that, I would like to thank you, Professor Pawelec, for the wonderful masterclass. Sorry, I just spoke a bit too soon. We have a question from Satoshi. So yes, you can please go ahead and ask your question. If you'd like to start your video as well, you can do that.
I'm sorry. Hello, my name is Satoshi. I'm studying at the University of Tsukuba, master's first year. I missed the time, so I only joined after the your presentation. So excuse me if I'm doing the silly question. I'm also doing optical visible spectroscopy with high-speed camera, and during that I have difficulty in isolating some lines such as NH and nitrogen, which is located at 336 nanometer. And how do you solve that kind of problem? And one more, the second question is, sometimes if the density of the plasma is very high, I think we need to consider the absorption when we are doing the visible spectroscopy. How do you tackle this problem? Thank you very much.
In the jet Tokamak, let's start with the second because it's shorter. In the jet Tokamak, mostly the so-called self-absorption is on the atomic lines, and mostly it is considered for Lyman lines, meaning Lyman series of hydrogen. This is the only one which we really have in the divertor in the sufficient number to get a significant self-absorption. So as far as I know, in the fusion machines, the self-absorption isn't for us very important. Well, it is very important for those specific lines, but mostly not for, even for Balmer series, they always tell me that not much. So so the first one was the problem of distinguishing the different molecular things from nitrogen, I think.
Yeah, very like a cross lines.
Yeah, well, you will have them all because, well, at least what we have been observing in jet when we put nitrogen in it, because so let me show you for the moment. I have here, here is the nitrogen hydride, the high resolution spectrum of nitrogen hydride, 336 nanometer. We were measuring it, and we had also N2 plus, which is not here. The strongest N2 plus is 390 nanometers, and those are observed here. And if you have a broad camera, you will have them. You will have more of them. What we didn't have in jet was N2 in itself, which is the molecule which is at 330. And how to distinguish it with the filters that you have for cameras, I don't really know. You would need very specific filter, very narrow band, because they are very close. As I said, in jet it is not a problem because I think in Aztecs as well, we don't really see the molecular nitrogen spectrum. We see only the NH, and we see N2 plus, which is slightly further into the longer wavelength. That's why we don't have the situation when they overlap. One thing, if you are interested, for example, if in N2 plus, you can get also different molecules that are there. There is also the CN molecule. If you have carbon anywhere, you can but this is for N2 plus, not for NH, not for N2. NH and N2 are very close to each other, and then N2 plus and CN. This is another band. I have observed CN even in jet. We don't have much carbon, but for the very low energy pulses, I have observed the cyanide molecule as well.
Oh, I see. Thank you very much. Right now, yes. Yeah, for the first question, it was very interesting that only even in jet Tokamak, basically you only need to consider like Riemann lines. That is very interesting. And for the second question,
the others are not self-absorbed. Simply, we have them, but they are relatively not absorbed.
I see. And yeah, for the second question, yeah, I think this is exactly what I was like concerned. And thank you very much for the answer. I'm currently using a high-speed camera, so the like full width half maximum for the filter is 10 nanometer. So it's too wide to distinguish with.
To distinguish NH and N2.
One last question is like, how narrow should it be for the filters for spectroscopy?
The NH peak is relatively thin. You can see here it is around 2 nanometers. So and I think the N2 would be somewhere here. So 2 nanometers probably would cover the peak and exclude the other.
I see. 2 nanometers. Thank you very much.
We got technical, yes.
Well, that's the purpose, right? So really nice to hear some questions and some wonderful interaction. So yeah, then if I don't see any other hands raised while I'm speaking, trying to close the session, I really like to thank once again Professor Pawelec and also all the attendees. Thank you very much, everyone, for joining, and we will keep seeing you around.